Hey, good morning, calculus students. Today I want to talk about the different integration techniques. So for those of you who do have hard time to find out which integration formula or technique or things that we need to apply for, so what should we do? How do we determine which part, which strategy, or what kind of method or what kind of formula that we need to find out? One thing that you need to do, you need to recognize the pattern of the given integrand. So from the given integrand, we can find out whether we can use the basic formula or we have to use like integrated by part, partial fractions, use substitutions or any kind of strategy. So now we'll take a look at this. Okay, so this one is section 7.5, strategy for integration. So in this section, we present a collection of miscellaneous integral in random order. Okay, so we just randomize all kind of integrals, and then just want to confuse you a little bit first, and then we'll determine what kind of technique to apply. Okay. So a prerequisite for strategy selection is a knowledge of the basic integration formula. So make sure that you guys need to recognize, not memorizing, but recognizing all the basic formula. So what is the difference between memorizing and recognizing? Recognizing is like knowing the structure of the pattern, the formula, and so when to apply, how do we apply, what's the appropriate situations that certain things need to be used for that integrand. Memorizing it just like showing the pattern. Well, that's just the form, but a lot of students memorize the formula, but they don't know how to apply them. So that's considered memorizing. But recognizing it, I do see the pattern with like a certain formula which can apply to. So, and that's the main difference. Okay. So now here the basic integral formula. So those are the ones that you have to recognize. So integrals of x to the power of n, power formula, the power rule. Integrals of 1 over x. So once you're integrating 1 over x, so then that'll be a natural log of absolute value of x. The way you can check the work is just by taking the derivative on both sides using part 1 of FTC. And then number 3, exponential integral. And then this one, the constant base exponential integral. And also the trig functions, sine, cosine, secant square, cosecant square. So those are the classic one. Secant tangent, cosecant, cotangent, integrals of secant, which is natural log of absolute value, and then cosecant, and then natural log of absolute value. So make sure that you guys need to recognize all of this, especially for those students taking my calculus class. So those are the one I normally test my students, once a week or maybe every other week. So those are the basic formula you need to recognize. And 13, integrals of tangent, integrals of cotangent. Sinh and cosh, don't worry about those two. I mean, you can recognize them, but the things that we rarely use them, unless you want to major in civil engineering or any like architect, major courses. And then 17, 18. Okay, so the inverse of trig functions once you integrate it. Again, you see the pattern here. So it's the sum of a perfect square, the sum of two individual perfect square, the variable with the constant, and this one is 1 over square root of a squared minus x squared. So it's kind of like a Pythagorean theorem, with the right triangle given. And then this one, once you integrate it, so it's a inverse of sine of x over a. Definitely I can show the proof for this type of formula, but the things that those are the ones you have to recognize. You don't want to do the proof to derive the formula during the test. There's no time for you to do that, okay? And then 19 and 20, those are the special ones. So 19 and 20, they're optional. Formula 19 can be avoided by using the partial fractions. So you don't want to recognize it, or you have hard time to recognize this one, you can always integrating it by using the partial fractions. And trigonometric substitution can be used instead of formula number 20. So 19 and 20, that's why I put the heuristic right here. So you don't need to recognize those two. And now the strategy for the integration. So once armed with this basic integration formula, you might try this strategy. So try to simplify the integrand all the time if that's possible. And then number 2 for inobvious substitutions, so make sure that you try to do some substitutions. And then number 3, classify the integrand according to its form. And none of those strategies work, try again. Look for something else, but try to do it slowly. So simplify the integrand. So that's always the first thing you want to try. So sometimes the use of algebraic manipulation or trigonometric identity will simplify the integrand and make the method of integration obvious. So something like this. So integrals of square root of x times the quantity of 1 plus root x dx. So you can always distribute. And then once you distribute, you can integrate it each term individually. And then the other one, tangent of theta over secant square of theta. So this one can be written as sine over cosine. And then 1 over secant square, it's just cosine square of theta. And then reduce, cross cancel. We do have integrals of sine theta, cosine theta, and which is the double angle identity. So we can simply integrate that integrals of sine of 2 theta. Just making up the number 2, the coefficients. Okay. Another one, so for the quadratic, the perfect square quadratic binomial, so we can always expand it and then try to integrate it term by term. And also we can apply the trig identity for this one, sine square of x plus cosine square of x, then that's 1. And then step 2, look for obvious substitutions. So try to find some u substitution for anything if the integrand looks very complicated. So for instance, the integrals x over x squared minus 1 dx. So notice that u equals x squared minus 1. And then we can solve for x by using the u substitution, or using that, take the derivative both sides, so we can find out that x dx is actually part of the derivative of du on top. And then just multiply the missing element. And also we can solve for that x in terms of u by using the algebraic manipulation. So we use the u substitution. And also we can use that for the partial fraction. And then step 3, classify the form. If step 1 and 2 have not led to the solution, so we take a look at the form of integrand. So sine x, cosine x, the product. So we use the product to sum. Tangent and secant, so that's kind of related. Cotangent and cosecant, so we can use those formula. Or we can use the trigonometric substitution. If that's a rational function, so we can use that integration by partial fractions. Or we can use that integrated by part if you find out things that cannot be integrated, so such as the trigonometric, exponential, or any kind of logarithmic function. So try to use that integration by part technique. And also the radicals, so if you see any kind of weird radicals, so we can always use certain kind of substitution. Okay, so like u equals and root of square root of ax plus b, or if you see the pattern like square root of plus minus x squared plus minus a squared occur, so we use the trigonometric substitutions according to that section 7.3. So it's all about the inverse trig function. If you see anything like an nth root of ax plus b, so we can use that the u substitutions. So step 4, try again. If the first step, do not work for anything at all, so just remember any basic formula or any method for the integration, substitutions, or integrated by parts. So even if no substitution is obvious, so some inspiration of ingenuity or even desperations, so may suggest an appropriate substitution. So try to use some kind of substitution, just play around with the integrand, with like certain u or w, or perhaps you have to use the combination strategies. Okay, so integrated by part. So now let's take a look at that, some of the example first. So this one you have to actually manipulate the integrand. So integrals of dx over 1 minus cosine of x. So what we're trying to do here, if you try to use that to use substitution, there's no du on top. And we cannot just simply make up the functions. So instead of doing this, so we try to multiply the top and the bottom by the conjugate. So the purpose of using the conjugate, so we can use the trig identity for the denominator. Because 1 minus cosine square of x, then that'll be considered sine square of x. And then from here, we can separate the terms. So it's easier to separate those terms individually. It's easier to integrate the term by term. Okay, so instead of integrating the whole integrand, with dx, so it's better to separate them out. So we got 1 over sine square of x, then that'll be cosecant square of x. And then cosine of x over sine square of x. So for that part, we can use the u substitution. And so another strategy is that related with the previous problem. So something that you did already, so you probably want to look back and then find out any obvious techniques that we can apply. So for instance, so let's say we do have integrals of tangent square of x times secant of x dx. So this one, basically, we can just separate them. So we can use that tangent square of x, so that equals secant square of x minus 1. So once you do that, so this one is just the Pythagorean identity. So that means the integral can be replaced by secant square of x minus 1, the quantity, times secant of x. And then distribute, so you end up with integrals of secant of x to the power of 3 minus integrals of secant of x. And here's the one that I was talking about earlier. So sometimes 2 or 3 methods are required to evaluate the integral. Okay, so now let's look at this one. So if you see anything like tangent x to the higher power, cosine of x to the higher power, so this one we can just rewrite it with that integrals of tangent of x to the power of 3 times secant of x to the power of 3. And this one is just like the trig substitution we talked about in 7.2. So it's now of the form with that integrals of tangent of x to the higher power, secant of x to the higher power. So we used the advice in session 7.2. Okay, so another technique for this. So try to use the substitution. So tangent can be written as sine over cosine. So we can do that as well. And then from here, and then we try to use the split. So let's say that sine x to the power of 3, we can just split into sine square of x and then sine of x. So for sine square of x can be written as 1 minus cosine square of x. And then using the strategy, the u substitution technique. Okay. So once you use the u substitution technique, so we can separate those terms. Well, this one we just swap those terms, so negative, negative, so that turns out to be positive. So that's why the integrand is written as u squared minus 1 over u to the power of 6. And then separate those terms out, so we can integrating each term individually. So for things that's like e to the power of square root of x, so this one we can set that u equals square root of x. And then solve for x, so x will be u squared. And using the u substitution technique, so we do have this. And then this one is the pattern of the integration by part. Because that integrals of e to the power of u, it's just the same thing. And then derivative of e to the power of u, it's going to be the same kind of function again with the chain rule. So we try to use the integration by part after you set up the u substitution for this. Rational functions. So no algebraic simplification or substitution. It's obvious. Excuse me. So step 1 and 2 don't apply here. So the integrands of rational functions, so apply the procedure of section 7.4. And remember that the first step is to divide, because that the power on the top, it's greater than the power down the bottom. If the power on the top is less than the power down the bottom, that means you want to do the partial fraction decomposing. procedure, okay? So what about something like this? So this one we can use that to use substitution. So u equals natural log of x, because that's differential is du, which is dx over x, and it's already given. So which occur in the integral. And something like integrals of square root of 1 minus x over 1 plus x. So this one, if you try to use the u substitution, that means it's going to leading to a very complicated rational functions. So it's easier to use the algebraic manipulations. So what we can do with this, we can separate the radical top and the bottom. And then down the bottom, we can just rationalize the numerator. So once we multiply square root of 1 minus x, top and the bottom, so we end up with 1 minus x over square root of 1 minus x squared. And then for the denominator, so this one is just considered, it's a common denominator. So for the numerator, we can separate them. And then from there, you see the pattern. It's the inverse of sine. And then the other part of it, it's just like a u substitution. And then we can just integrating it. So then that would be square root of 1 minus x squared plus constant c. So here's the questions you guys might come up with. So will our strategy for integration enable us to find the integrals of every continuous functions? So far with the technique that we have, we can use that to find out the majority of the integrals, to evaluate the majority of the integral. But once you deal with like a very complicated, crazy functions, no. So there's another calculus class, it's called differential equations. So you're going to be learning like all those advanced techniques to integrating any kind of homogeneous equations, high order power, any kind of polynomial, high order power polynomial, or any kind of crazy complicated structure functions. But so far, this one is just given as the normal integrand with all kind of functions, all the transcendental functions such as exponential, log, trig, inverse, any kind of pattern regarding the Pythagorean trig substitutions, integrating by part for the rational functions. But anything that's considered more complicated, or like a high order power, or with y prime, with y double prime, so that it's going to be taught in differential equation. So again, so one thing that I emphasize, I should use the keyword elementary functions. So all those type of elementary functions. So those are the one we just want to focus on. But once you get into like y prime, y double prime integrations, then that's going to be in calculus differential equations. And for my personal preference, I'd like to call that it's calculus 4. And for those you might be wondering what calculus 3 is, calculus 3 is a multivariable calculus with x, y, z. It's all about vector, slow field, vector fields, triple integral, things like that. Okay, so elementary function, if f is an elementary function, then f prime is an elementary functions. Okay, so obvious. So something like this. So we know that part 1 of fundamental theorem of calculus, f prime of x is the same as e to the power of x squared. Replacement. So f of x equals e to the power of x squared has an antiderivative of capital F. So we skip all through this. So elementary function, those are the ones that we've been talking about. So e to the power of x over x, sine of x squared, cosine of e to the power of x, square root of x to the power of 3 plus 1, 1 over natural log of x, sine of x over x. And the majority of the elementary function do not have elementary antiderivative. Well, that's true. So that's why we have to use all the strategies. Or if this one cannot be integrated, so that means we have to use the graphing calculator. Okay, so that's it. So this one is all for 7.5. So let me know any questions and any concern that you have. So I'll see you guys next time. Take care.